All right, guys, welcome to vodcast 9.4. We're going to talk today a little bit about partial pressures. We're not going to go too massively deep into this, but I want you to get the idea behind it. And hopefully, by the time you've watched this video, you've run the sim a little bit and already figured out a few things for your own about partial pressures. So let's jump right into it. First off, partial pressures all revolves around Dalton's law of partial pressures. And really, it's pretty simple. I mean, basically what it says is that if I have two gases in a box, okay, so I stuff some oxygen and some nitrogen in the same box. What Dalton's law says is that the total pressure is equal to the sum of the two individual pressures. Okay, so what that would mean is that I would take my 79.9 here, okay, which is my nitrogen, and I would add that to my 21, which is my oxygen. And when I add those two things together, I get a total pressure of, in this case, 100.9 kilopascals. Okay, that is the total pressure. And so that's a pretty simple concept. What Dalton's law would further say is that if I added in another gas, that I would add that pressure in as well. And so that would be the same thing as this. That would count for those two. And then I would add in the argon's pressure as well. And once I added that, that would give me a total of something like, I'm probably going to mess this up, 101.4 kilopascals all added together. And this can go on for as many gases as you need. Now, why is that important? Because when you get to the EOC and you're working some partial pressure problems, you're not going to see the formula written as either of these two things. The way you'll see the formula written is like this. You're going to see P total, okay, or maybe just P, and it's going to be equal to P1 plus P2 plus P3 plus dot. Okay? And all that means is that it's just the sum of all of the gases you have. If you only have two, then you just add up two. If you have three, then you add up all three. Okay? If you've got 20, then you add up all 20 together. I mean, that's pretty much as simple as it gets. Now, how do we actually see this as a problem? Or more to the point real quick, let's look just a little bit about how this actually works. For those of you that ran the sim the other day, you should remember this a little bit. And so just remember the sim. You got a temperature here, pressure, all that stuff. And so I've got constant temperature here. And what I'm going to do is I'm going to add in 100 of the light. Okay. And we're going to give that a second and see what pressure it comes up to. Okay. You see the pressure is rising. And then it sort of jumps around a little bit. Now remember that the pressure is going to jump around a little bit because you get pressure from molecules bumping around and colliding with the walls of the container. So we're at about 0.52, 0.51, something like that. So I'm going to go back in and I'm going to add 100 of the heavy, and it's going to change again. Now you'll see it'll take a little bit longer because the heavies take a while to jump in. And what you see is that we've got a pressure somewhere around twice what it was with the light. And you're like, how does that show that it's, the two things added together? Well, just to show that, let's real quick, and this is probably what I should have done in the first place, let's just throw 100 of the heavy in and see what happens. Okay, and again, definitely takes it a second. Okay, they're moving a lot slower than the fast ones, so you see the pressure starting to rise. And so it's going to come out to be somewhere around 0.52, 0.53, 0.54. And again, if we add that 100 of the light back in, remember they're both right around 0.54 or something like that, pretty close. And what you'll see is that when we put them both in together, that we get a pressure that is basically the two of them added together. And if they're both 0.52, then this should be around 1.04 or something like that. And you're like, well, why is it 1.0? Well, really, they should have been both right at 0.5. But again, there's some variations as it hits and stuff like that. So there's a little bit of error, but not much. And essentially, it's the idea that as we put two different gases in together, that we add their pressures together. Okay, they're cumulative. They add together as we do that. Okay, so what does that mean for us in terms of actually working problems? Well, first off, the most common way to work a problem here is what we call the method of collection over water. And I think in some places, maybe even in your problems, I may have called it water displacement. Water displacement, remember, is about density. So it really should be collection over water. I mean, there is some water being displaced, but really collection over water is the best way. Now, what does that mean formula-wise? Well, that's going to give us a formula of this. Okay, total pressure is going to be equal to the pressure of the gas that we're collecting plus the pressure of the water vapor. Now here's the reason why. What we're doing is we've got a chemical reaction going on here. The gas is going to come up here. It's going to go through this tube and it's going to bubble through the water. And then up here, we're going to collect the amount of gas and water vapor. So this might be a eudiometer or something like that. And you'll note here that we have some water vapor. Okay, water vapor is always going to result. Some of the water molecules are always going to escape into gas phase because of the gas that comes out here. Now, the good news is that's always a constant. We can always find the water vapor pressure, okay, the P sub water, by using a chart. As long as we know the temperature. We just pull up a little chart, and you can just Google it online and say water vapor pressure, and you'll get a ton of different charts that'll come up. And what you see is that they've got temperature in degrees, and then they tell you what the water vapor pressure is at that temperature, and it's a constant. So if I look up, say, 19 degrees Celsius, it's going to have a water vapor pressure of 16.5 millimeters of mercury. Now, those units are going to be important. We'll talk about those as we work a couple of problems here in a second. But remember to look on the table. You've got some on the back of your homework. You've got additional sheets that you'll have. Now, on the test or on the EOC or something like that, you won't have probably the table given to you, but they'll just tell you in the problem what the water vapor pressure is. So just remember to look out for that when you're doing this. So here's a sample problem. A student collected oxygen gas, and I should say collected, oxygen gas by water displacement, again, over water, at a temperature of 15 degrees Celsius. The total volume is 188 milliliters at a pressure of 92.3 kilopascals. Okay, so what do we have here? Dalton's law. And how do I know it's Dalton's law? As soon as you saw water collected gas by water displacement or over water, you should immediately know that it is a Dalton's law problem. Okay, so here's my formula. My unknown gas is oxygen, water vapor pressure. Okay, and I'm at 15 degrees Celsius, so I'm going to jump over to my table. Whoops. I'm going to jump over to my table. We're going to scroll down to 15 degrees, and it's 12.8 millimeters of mercury. Okay, so I'm going to write that down. The H2O pressure is 12.8 millimeters of mercury. Now, I don't really want millimeters of mercury. Okay, since this is in kilopascals, I either need to turn this into kilopascals or I need to turn this into millimeters of mercury. It doesn't really matter which way. It didn't ask me for a specific pressure. So you can do either way that you want. I'm going to go ahead and convert my water vapor pressure into kilopascals. Okay, that goes back to the stuff that we did in 9.1. Okay, where we had that long equality that had a bunch of stuff, torr and millimeters of mercury and kilopascals and atmospheres. That's the one we're going to use here. And so I know that 101.3 kilopascals is equal to 760 millimeters of mercury. Okay, so we punch that into our calculators and we get, let me see here, 1.71 millimeters, I'm sorry, not millimeters of mercury, kilopascals, because that's what I'm looking for, right? Okay, so that number then is what's going to get plugged in right here. Okay, this number is my total pressure. Okay, so I'm going to plug those two things in. 92.3 kPa is equal to the pressure of oxygen plus 1.71 kilopascals. That's my water vapor pressure. Then we just got to do some algebra, right? And to get PO2 by itself, since this is added, we just subtract from both sides, right? Simple algebra. That's a 1.71, obviously. Sorry about that, guys. And we subtract that out, and we get 90.6 kPa. Okay? So pretty straightforward. I mean, nothing massively difficult about that particular problem. And really, about 90% of partial pressure problems that you guys will encounter in Chem 1 or even in Honors Chem 1 are going to come down to the same basic thing, that it's just you're missing one of the things to plug into Dalton's law. You plug in the stuff you do know, maybe look something up on a table, and then just subtract to get the other one. You might have to do a conversion. All depends on what it asks for. It didn't say anything specific. Had it said maybe atmospheres, I would have had to convert this and this both into atmospheres. But it didn't say anything specific, so I just have to convert them so that both of them are the same thing. Okay? Now, what would a more complicated problem look like? So let's read this problem. You collect N2 by water displacement. Okay, so again, nitrogen by water displacement at a temperature of 19 degrees. That's kind of my hint right away that I'm going to be using Dalton's law. Okay, so total pressure equals Pn2 plus the pressure of water. Okay, we're at 19 degrees, so again, we're going to jump over here to our table. Scroll down, 19 degrees, 16.5 millimeters of mercury. Okay, so let's write that down. Pressure of H2O is 16.5. It says millimeters of mercury, but if you remember from your conversions, torr and millimeters of mercury are the same thing. Okay, 760 torr equals 760 millimeters of mercury. So I don't really have to do a conversion. I'm just going to switch out the units because they're the same thing. Okay, and that's good because that means I don't have to do any conversions here. So I'm going to plug this stuff in. My total pressure of the system is 780 torr. Now you may be saying to yourself, hey Arnold, aren't you missing a bunch of these other numbers here? I'm going to come back to them in just a second, okay? We got to do the Dalton's law part first, and then we'll get to the rest of the problem. Okay? Wow, that is atrocious handwriting, which any of you all who actually watch the videos are quite used to at this point. Okay? So basically we're just taking 780 minus 16.5. That, of course, is going to give us, I'm kind of ashamed that I even looked down at my paper, 763.5 torr. Okay, now what? So what am I looking for here, first off? I mean, for once, I didn't actually even really look at what my unknown was. I mean, it says how many moles of gas. Now, as soon as you're doing a gas law problem and you need moles of something, the thing that should immediately pop into your head is that if I need moles, okay, and I'm doing a gas, the only thing that I have gas-wise that has moles in it is PV equals nRT, or the ideal gas law. Okay? N is moles, remember. P is pressure, V is volume, R is the constant, T is temperature. Remember that there are a couple of other pretty important things here that we have to do, which is that since we're using the ideal gas law and the ideal gas constant, my pressure has to be in atmospheres. So I'm going to go ahead and convert that real quick. 760 torr, right? 1 atm. Okay, that's a 1. And when we calculate that out, we get pretty close to 1. I mean, that's pretty close to 1 atmosphere, 1.004. I'm going to go ahead and keep that just in case. Our volume already in liters. And then remember, temperature has to be in Kelvin, so you just add 273 to that. So that's going to give us a temperature of 292. Okay, so I'm going to go ahead and just real quick, pressure, temperature equals 292 Kelvin. Okay, and then we're going to plug this stuff in. Okay, so pressure, 1.004 atm. Volume is 1.25 liters equals N. Ideal gas constant, 0.0821. I didn't write out all the units there. And hang on, we'll put temperature in here in a minute. Let me move some of this stuff over just a tad. Okay, and then the last thing we have there is our temperature of 292 Kelvin. Remember, if you've converted everything to atmospheres, liters, and Kelvin, you don't technically have to write this. It's probably good form if you do, but I'm trying to save some space, and it's kind of hard enough to read everything that I've written here anyway with my sloppy handwriting. So I thought I'd not clutter it up anymore. Okay, and so now it's just an algebra thing. And remember, you're basically going to divide both sides by these numbers. Okay, so both sides by that, 0.0821. Okay, 292. That would be a 292. Okay, same thing over here. Going to cancel this stuff out, right? 292. That cancels, that cancels. N is now by itself. We punch all this stuff in the calculator and we get 0.052 moles of N2. Now, that's a little bit more complicated, but not really a lot. I mean, we already knew how to do the ideal gas law, so it's just really one more step to do partial pressures. They could have even asked you for grams or something like that here, or like one of the ones on your practice problems, you could have had to take this moles and then plug it in somewhere else. Maybe you had to plug it in to another PV equals nRT at a different temperature, pressure, or whatever. But it all works out this way. If you got a combination of gases, then you do Dalton's law, and then you plug in and solve for the other stuff. Okay? Hope that worked out pretty well for you guys. That'll be it for this vodcast. Make sure that you're keeping up with all of these and that you're keeping up with all the assessments and all the practice problems. Thanks, guys.